All right, next reaction. Let's review real quick. I think you have seen this reaction before. Am I right? You have seen this reaction in alkyne. So we reduce alkyne to a trans alkene. Remember the mechanism? If not, let's review. Okay. So we add sodium metal in liquid ammonia. So the reaction goes like this. I mean, the mechanism goes like this. This show single electron transfer. So the arrow, I'm going to use the fishhook arrow. Okay, just one-headed arrow right there. Now let's take a look what happens. So start with an alkyne. There are 2 pi electrons right here, and there's 2 more down here. But just look at the top. Sodium will donate just 1 single electron. Okay, so this pi electron and electron from sodium will pair up, and you have a lone pair. The other pi electrons stay on that carbon like a radical. Okay, and from here, you're going to have 2 sources of the electron density. What happened is, here's the stereochemistry come from here. These 2 electron density, they repel. All right, so trans is a preferable isomer than cis. That's why at the end, you have trans alkene. Okay, all right. Now we have this reaction for benzene ring we call Birch reduction from author John Birch. He's an Australian organic chemist, came up with this reaction. Look at what happened here. We add sodium, like sodium metal, in liquid ammonia, just like the previous reaction you saw. Okay, and use methanol as a core solvent. Let's take a look at the mechanism. So sodium donates 1 electron, group 1 donates 1 electron to a benzene ring. Okay, so 2 pi electrons, 1 pi electron pair up with a single electron from sodium, you get a lone pair. The other pi stay on that carbon, you get that. Look like a radical. Now, lone pair and a radical, they are next to each other and they have repulsion. So the best isomers, not isomers, the resonance structure is these 2 are far apart. All right. Now, next step, so we take the solvent. So methanol will act like a proton source. Protonation, you get the hydrogen up here. The other one, so you can pair up, will pair up with 1 single electron from another sodium. All right, so you get a lone pair down here. And same thing, protonation from a solvent. Okay, ta-da! All right, so basically we reduce 2 carbons that are opposite from each other, para position, basically. All right, you can do this with naphthalene as well. All right, take a look. Sodium metal, liquid ammonia, ethanol, diethyl ether. That's a core solvent, basically. They have to do a reaction at negative 78 degrees. So, yeah, you're gonna reduce 2 carbons that are opposite from one another. Okay. Quick question about the condition, the temperature. How would you set up as low as negative 78 degrees? Anyone knows? Some of you might have used rotovap, right? In the trap rotovap, we add dry ice and acetone. The combination between dry ice and acetone gives you negative 77 degrees. Okay, it's really, really cold. Often chemists use Dewar flask because it got a thick wall. All right, so this thick wall will act like a semi-insulated container. So the setup looks something like this. So we have a reaction flask, we have acetone and dry ice, and we have on the Dewar the container. Okay, can we go lower than negative 78 degrees? We can. In the laboratory setting, very popular, we use liquid nitrogen, negative 195.8 degrees C. Really, really cold. Okay, you will freeze off your toes, your finger right away. So try not to touch that if you get a chance. Okay. All right. So a little bit more about Birch reaction. We're going to move on to the ratio selectivity of Birch reduction.